Hi, I'm whitebox from Adelaide Uni. Today, I'm excited to talk to you about our recent work. Due to the impressive performance of deep learning models on a variety of vision tasks, they've been deployed in many real-world systems and increasingly being offered as a service from many providers, such as Google, Microsoft, Amazon, and so on. And now, application developers can easily incorporate intelligence in their own products. However, recently, many researchers have demonstrated that deep learning models are vulnerable to imperceptible perturbations called adversarial attacks. For example, adding an imperceptible perturbation to an image of stop sign can cause the stop sign to be classified as a traffic light. In fact, on industrial systems, for example machine learning as a service, attackers have no knowledge of a model, and access may be limited to only the model's decision via access interface. As illustrated in this figure, using only the model's decision to construct adversarial attacks, called decision-based attacks, presents a practical threat model for the deployed systems, because the adversaries are still able to exploit very limited access to craft adversarial example. However, this also leads to a such challenging scenario. In general, in a decision-based threat model, as illustrated in the figure, an attacker has only access to a model's decision without any knowledge of that model, and has at least one sample from a target class called a starting image, but doesn't know what is the best one. The attacks in the decision-based setting can be formulated as an optimization problem 1 that minimizes the distortion between source and starting images, such that the perturbed image is still classified as a target class in a targeted attack. This problem can be illustrated by this figure. The attacker aims to search and make the starting image switch side move towards and look similar to the source image stop side, but still classified as a speed side. In the decision-based setting, only model's decision is available and accessible to adversaries, so it's impossible to apply gradient methods directly. Therefore, many gradient estimation methods have been proposed to solve the problem. However, the existing attacks suffer from the following problems: sensitivity to the starting image and entrapment in a local minimum. Therefore, we spend our efforts to understand the problems of gradient estimation methods and develop a more robust and query-efficient attack by answering 3 research questions. The first research question is how to assess the fragility of decision-based attacks. To answer this research question, firstly, we empirically define a so-called hard case to an attack as a pair of source and starting images, which the attack fails to yield an adversarial example with a distortion below a desired threshold within a query limit. For example, this figure shows that even with 100k queries, a solution based on a gradient estimation method doesn't improve the distortion of the adversarial example for a car classified as a dog. To assess the fragility, we conduct an exhaustive experiment to evaluate 3 state-of-the-art decision-based attacks, including hop, skip, jump, sound optimization, and barrier attacks, over all correctly classified samples of evaluation sets of 0-10, and aim to flip the prediction of every image to 9 target classes with a query purchase up to 50k, collect all the so-called hard cases for each method, and categorize them according to source and target classes. The figure shows that there are a lot of hard cases, and 3 state-of-the-art attacks aren't uniformly effective against all pairs of source and starting images. This result leads to our first observation about hard cases. In decision-based setting, specific classes and samples from these classes are more difficult to attack than others. It happens to all state-of-the-art decision-based attacks and shows that these methods aren't robust on these hard cases. To answer the research question 2, what is the impact of source and starting images on the success of an attack? We empirically search and construct 2 hard sets A and B from 0-10. For each hard case, we have 1 source and 10 starting images for the same target class. Evaluate hop, skip, jump, sound optimization, and barrier attacks on these 2 sets. In the scatter plot, The sign of a bubble denotes the distortion variation, and y-axis represents the average distortion. The result shows that, to all the attack methods, most bubbles are high and bubble size is low. Based on these results, we can see that these attacks are highly dependent on the starting image to find low distortion perturbation. The results also lead to our second observation about attack initialization. The ability of an attack method to find a low distortion adversary example with a given query purchase is dependent on the starting image from a target class. Currently, there is no effective method to determine a good starting image prior to mounting an attack. One of the pitfalls of gradient estimation methods is the potential for an algorithm to get trapped in a bad local minimum. To understand and illustrate the underlying cause of this pitfall and our observation mentioned above, we use three state-of-the-art methods to attack a toy model, whose descent boundary is illustrated in the figure. Source and starting images are represented by a pair of source and starting points in this figure. These attacks result in different final solutions, denoted by yellow triangles. We ran this algorithm 100,000 times. Post-optimization and boundary attack failed to find the global minimum, represented by the red star optimal point, while hop skip jump only found the global minimum with only 2.5% of success. Problem from research question 1 and 2, as well as the entrapment problem, lead us to the research question 3, how to avoid the pitfalls of gradient estimation methods and construct a robust and query efficient attack to achieve low distortion adversarial example with any starting image. We observe that all current attacks alter a whole image to force a perturbation. So to tackle the third research question, we take another approach and introduce an analogous randomized block coordinate descent method named block descent. This approach targets localized changes to affect convolutional filter outputs and modify color values in multiple square regions called blocks simultaneously and in different color channels of an image. This intuition can be illustrated in this figure with multiple beta blocks. We observe that modifying multiple blocks can mimic salient features of the starting image and embed them in the source image to fool the classifier. For example, perturbation heat map in this figure visualizes the normalized perturbation magnitude crafted by different attack methods, while we still see the pattern of the entire starting image in the perturbation crafted by other methods. The perturbation yielded by our methods concentrates on the salient area illustrated by red cam, even though our method doesn't exploit the knowledge of salient regions to generate this perturbation. Furthermore, we observe that the gradient estimation methods are effective in two cases: the initial stage of the optimization, when gradients are sufficiently large to be estimated effectively, and at close to the source image, when small changes and refinements facilitate a descent to the optimum. As a result, we derive a robust hybrid method named RamBoAttack that incorporates block descent with other optimization frameworks to improve both query efficiency and distortion in such hard cases. Interestingly, RamBoAttack potentially redirects to escape from the entrapment in a local minimum by taking a path along some coordinates towards a source image. Therefore, it partially prevents the entrapment problem encountered by gradient estimation methods. To understand and illustrate our intuition, we executed RamBoAttack over 100,000 times against the toy model as we did for all the state-of-the-art attacks, particularly when the first gradient estimation methods get trapped in a local minimum represented by green nodes. Block descent will take over to move away from that entrapment represented by blue nodes. Finally, the second gradient estimation method is applied to refine the adversary example and move closer to the source point represented by orange nodes. We observe that our attacks always find the optimal or near optimal solution. In particular, we illustrate RamBoAttack through three different stages. Firstly, a gradient estimation method is applied to alter a whole static image, for example lamppost. In practice, we can choose half skip jump or side optimization method for this stage. When half skip jump or side optimization no longer makes any progress and may get trapped in the local minimum, block descent will take over and modify multiple blocks of an image concurrently to move away from the entrapment. Finally, another gradient estimation method is employed to refine and yield the final adversarial example. We observe that at this stage, side optimization outperforms half skip jump, so side optimization is our choice. In this section, we demonstrate the robustness of RamBoAttack. In the same experiment for research question 1, the result shows that the number of packages for RamBoAttack is less than other state-of-the-art methods across different pairs of source and target classes. In general, RamBoAttack is more robust than other state-of-the-art methods. We also evaluate the dependencies on chosen static images of RamBoAttack using the same experiment for research question 2. We can see that our RamBoAttack consistently achieves smaller distortion mean and variation than other state-of-the-art on power access ANP. Therefore, RamBoAttack is less dependent on chosen static images than other attacks. In this experiment, we compare the performance of RamBoAttack versus other state-of-the-art methods on the access ANP with query limit of 50K. The result shows that the RamBoAttack obtains lower distortion mean and median than all other attacks. For attack success rate at both 25 and 50K query limit, our method outperforms all the state-of-the-art methods by far across different distortion levels. Likewise, on the access selected from ImageNet, the result demonstrates that RamBoAttack outperforms side optimization and half skip jump in terms of distortion and attack success rate. In conclusion, our study is the first systematic investigation of the 3 state-of-the-art decision-based attacks to understand their robustness and fragility, propose a novel attack under a difficult but pragmatic decision-based setting, which is more robust than 3 state-of-the-art attacks, provide new insights for crafting adversarial perturbation, and illustrates clear correlation between perturbations and salient regions on static images.